So the f and g that we saw in the previous slide, right? The next slide we are going to introduce some new terms, right? So I'm going to call this entire thing as v plus, right? Just a notation. We'll see why I'm associating the plus and minus signs, right? I'm calling b times the function g as v plus, right? And a times f as v minus. So this essentially becomes 1 over square root of L by C. I notice that the first term Bg is V plus and V minus. Okay. Instead of having to write A times Ft plus x square root of Lc each time, I'm just going to lump that as a single term and represent the entire thing as V plus and V minus, right? So when I do that, I get something that I can write in a very short way. So I have V of x plus t as V plus V minus, and I is V plus divided by Z naught minus V minus divided by Z naught, where Z naught is square root of L by C, right? And x square root of LC, I am writing it as x by V, where V is 1 over square root of LC. Okay. So just some notations. It will quickly become clear why I want to make these changes, right? But I want to give some insight, right, as to why the equation is called wave equation and the solutions to these wave equations are called waves, right? So what is this wave? I believe that this is exactly the point where students need to pause and take some time, right, to understand what is this waves, right? I'll try my best to give you some sort of a notion, right? Because I have seen in the past when students try to get past this section, they start to think that the voltages and currents themselves have changed in some way, right? That it is no longer the volts and amperes that they were used to, and now they are these waves, which could be a different entity. So all that is not true, right? So voltages are still the way that we have been taught what voltages are. If I were to give you two separate spatial points, I can measure the voltage difference between those 2 points. And how would I do that? Perhaps take a multimeter and try to measure the voltage between those 2 points, right? Similarly, current flowing through a wire is exactly the same definition as before, right? The only thing that has changed is that these voltages and currents are now functions of both the length along the transmission line as well as time, right? So there's one more independent variable that's coming in. Notionally, the sense of voltage and current has not changed, right? Although the next few slides is going to try and say that voltages are waves or we are seeing waves. Try not to cloud the original definitions of voltage and current due to that. Okay. So now we'll try to quickly understand, right, why I put plus for this argument and why I put minus for this argument, right? So remember the t minus tau and the t plus tau. I have chosen to put the sign plus for the t minus x square root of LC and v minus for the t plus x square root of LC terms, right? So I want to try and give you a picture of what is happening, right, to this function when t and x come together in pairs in this form, right? That is t minus x square root of LC and t plus x square root of LC. Let's try to take an example and try to understand what's going on. Okay, remember, voltage and current are now functions of both x and t. So I actually need a three-dimensional plot. Right? X and t are independent variables, and my voltage is the observed variable. Right? So if I were to say that the voltage at, so this point here, let's call that x equals 0 and t equals 0. Right? So at a particular location, which I call x equals 0 on the transmission line, I essentially measure the voltage at some time, and I set that time as t equals 0. Right? So let's say I measure at that particular instant some voltage, say 1 volt. Okay, I measure 1 volt at some location x equals 0 and t equals 0. So remember that this v plus t minus x by v, right, any function could satisfy as long as t minus x by v come together. This is one such function, right, where the function just takes up a value at a particular x, right, and everywhere else along the transmission line, if I were to measure the voltage, it is 0, right. So it is sort of like a delta function, right. So I have voltage just defined at one particular x value, right. So now I want to see how this evolves over time, right. So when I ask you v plus of t minus x by v, right. So at x equals 0 and t equals 0, I am saying that this function value is 1 volt, right. So I am going to say t equals 0 and x equals 0. This is 1 volt, right. So now say for example at distance, right, say capital or small l, right. So I want to know, so remember that v plus of t minus x by v at t equals 0 and x equals 0 is 1 volt. For all other x's, the voltage is 0, right. So now if I were to put x equal to some small l, right. So this is to say that v plus of 0 is 0, oh sorry, is 1 volt, right. V plus of 0 is 1 volt. So now if I want to know v plus of t minus L by v, right, if this had to be 1 volt, right. So I have sort of injected 1 volt at the location x equals 0, and I want to know when this 1 volt will arrive at the location L along the transmission line, right. So I am basically asking the same question, that is, when does this argument become 0, right? Why am I doing that? Because only v plus of 0 is 1 volt, right. So v plus of any other number is essentially 0, right. So if I want this 1 volt to appear elsewhere, I would need this argument to essentially go to 0, right, which is to say that v plus, the argument of v plus, which is t minus x by v, goes to 0 at some other time for a different location, right. So for a positive location L, right, when can I say that this 1 volt will appear at the position L, it is when the argument of this function becomes 0, right. So, at t equals L by V, right, we have V plus of 0, which is 1 volt, right. So, I can say at a time L by V later, right, that this 1 volt pulse has essentially moved from x equal to 0 to x equal to plus L. Okay, I hope this is clear. So, initially I launched a pulse voltage of height 1 volt at a location which I called x equal to 0 and at a time t equals 0, and I am trying to follow where this voltage is going. If it were to follow the function v plus t minus x by v, right, and I notice that this function, right, as time were to progress, or if you want to say that where is this voltage going to be 1 volt, right, I notice that the pulse is moving to in the positive x direction. Okay, so the pulse which was originally at x equal to 0 is moving to locations of L and 2L for positive times, right. So, at t equals L by V, it has reached the position L, and for t equals 2L by V, it has reached the position 2L, right. Right. So, it is sort of traveling along that line, right, the pulse, as you will. Okay. So, this is what we mean by a finite time delay, right, or a finite speed of light delay when it comes to voltages and currents propagating along a transmission line. This V plus t minus x by V is a function that is capturing the movement of the voltage from x equal to 0 in the positive x direction, right. So, when the relative signs between t and x by v are opposite, we call this a positive going wave, right, or the voltage which when initiated at x equal to 0, v plus function captures this voltage going to positive x values at positive times. Okay, this is why we call this v plus, right. For the direction in positive x, the voltage appears in subsequent times, right. In future times, I can expect the voltage to go to higher and higher positive x distances, right. That is why we use the term plus in the v t minus x by v, right. So, for the f of t minus x by v, we are using the plus notation because it is going to positive x values in future times or positive times, right. So, similarly, if you look at the t plus x by v, you will notice that for positive times or future times, the pulse or the voltage is actually going in the negative x direction, right. So, let us quickly look at this is now my V minus, this is my x equals 0 and t equals 0, right? And I say that V minus of 0 is 1 volt and 0 volts otherwise. For all other arguments of V minus, the voltage is 0, right? Except for at the value of 0, V minus of 0 is 1 volt, right? Now if I were to look at what this pulse is doing, this is my positive x direction, this is my positive time direction. If I ask myself for some future time, right, where will this voltage be non-zero, right, or where is this 1 volt voltage going to be for future times or positive times, right? So let's say at t equals L by B, same time intervals as we saw in the last slide. So the argument t plus xyb becomes 0 when x is equal to minus vt, right? So at t equals L by B, I can find the voltage to be 1 volt at x is equal to minus L. So if I have a function whose argument is t plus x by b, that is the sign on t and x by b are the same, right? Yeah. Such functions, if I look at how the voltages evolve, right, I am noticing that the voltage essentially moves in the negative x direction for positive times in the future, right? So you can basically compare and contrast the two functions that make up the general solution to the voltages and currents that come from the wave equation as some sort of emanation, right? So if I have some particular voltage at some particular location, V plus function denotes that voltage basically propagating in positive x direction for future times, and V minus is a function that denotes this voltage's movement in the negative x direction for positive times, right? So hopefully even in the future when we start looking at many situations where you're expected to estimate voltages and currents, if someone were to ask you whether this is a voltage that is going in the positive x direction or in the negative x direction or what is the direction it is going, try to look for this pair, right? So t and x by v, and see how they appear in the expression for voltages and currents, right? And see the relative signs between t and x by v. If t and x by v come with the same sign, that is t plus x by v, it is representing, the function is representing the movement of voltages and currents in the negative x direction, right? Whereas if t and x by v come with opposite signs, like t minus x by v, then the function v plus t minus x by v denotes the movement of voltages and currents in positive x direction for future times, right? So you can kind of extract whether a particular direction is being followed by just looking at this argument of this function, right? So even now I feel like this wave solution, wave functions are still a concept that takes some time to understand, right? Because language, right, is often a barrier. So our common speaking languages like English, Hindi, or whatever be the languages that you speak at home, these form a barrier to understanding some concepts in science, right? So when I say that I am walking, right, or my friend is going from here to there, right, we often use nouns, right? So we say that some object or some person is moving from A to B, right? Now when I say that waves, right, represent some movement, right, the first question is what is moving, right? So I think this is where the concept gets hard, right, to wrap around, take some time, but hopefully there are some analogies that I can try to depict to say how our language fails in attempting to say what is being observed, right? So in front of you is essentially a small setup that I've created in the lab. It is actually called a Shive wave generator, right? Dedicated to John Shive, who came up with this. So essentially, there are videos on YouTube that you can see about Shive wave generator as well. So here, it is a depiction of a mechanical wave, right? So there is a there's a very thin wire at the center, right, of this contraption that is made out of steel, and this wire can be twisted, right? So when I twist the wire from one end, this twist will actually propagate along this wire, right? This is a mechanical wave, right? And to slow down this torsion or twist, we've basically added a bunch of beams, right? So that now the twist has to essentially carry this beam weight, right? So it basically slows down the movement so that it is easy for students to observe the phenomena, right, in real time. So I'm going to play this video where I'm actually going to create a torsion, right, similar to sort of creating a voltage at a particular point on the transmission line, and I'm going to see something, right? I want you to observe the video and we'll make some comments about what is happening, right? And we'll try to answer the question what is moving, right, or what is waving in wave. So you can notice that there is a shape, right, where in a small region the beams have bent, right? So I originally bent the beams at the starting location, right, but those beams have now come back to the horizontal position, and now the beams that are bending are further down the line, right, and it seems to be moving to the right. Now the question is what is moving to the right, right? Are the beams themselves moving to the right? No, right? The beams are held stationary. In fact, they are soldered to the central wire that is under torsion, right? So the beams themselves are not moving, right? So another analogy for this is the Mexican waves. If you have seen stadiums, you can also Google what a Mexican wave is. The audience that are sitting in the auditorium, they basically raise their hands, right, or maybe stand up from their seats, but it kind of moves from one column to another column and feels like something is moving, right? The individual people or the cheerers are in their own seat locations, right, but it gives an appearance of something is moving, right? Even in the case that you're seeing in front of you, the beams themselves are not moving, right, but there is an appearance of motion, right? So we are saying that the beam bending is moving, right? Now, can bends move, right, is the question, right? So, this is where I would say that the language fails in trying to, because we are used to a particular notion where we cannot say a verb is moving, right? We can only say nouns are moving, like an object moves from left to right or right to left, right? But we never associate a verb of moving or jumping, right, as something that can move in itself, right? So remember that when we say wave, it is just trying to depict this phenomenon, right? Nothing in actuality is actually moving, right? It is an appearance of motion, right? What used to happen at some time in the past at one location is again reoccurring at a different location in the future. Okay, this is the best definition I can think of in the English language to portray what is happening and what we mean by or call as waves, right? So I'll repeat that. What happened, right? An event that happened at some time in the past at some location is reoccurring at a different location at a different future time, right, or current time, you can say. This apparent motion, right, is what we call waves. Okay, so when I say that voltages and waves, voltages and currents are now reminiscent of waves on, right, a transmission line, don't think that the voltages and currents are now some wave like quantity, right? That the original notion of voltage and current is gone, and when we are dealing with transmission lines, we have to think of it as waves. It's not so, right? Remember that at any particular location along the transmission line, if I were to take the central conductor and the return conductor, put a multimeter across those two conductors and measure the voltage, I will get the value of the potential difference between these two conductors at that particular location and that particular time, right? But in order to study the dynamics of what this voltage does once it appears on the particular transmission line at that location for future times, it is helpful for me to use the mathematics, right, to ascribe functions like the v plus and v minus that denote objects that are moving to the left and right by looking at the argument in order to estimate what the future voltages or where these voltages might end up at future times, right? So remember that waves, there is not really something that is moving, right? So the fields don't move. That's not the right terminology to say that electric field is moving or the magnetic field is moving, right? Some might also say that energy is moving, right? That's perhaps true, but the notion of energy itself for human beings is not that something easy to wrap our heads around, right? So I would say that this is sort of an apparent motion, right? So the motion is trying to essentially mimic the statement that what happened at some particular location in the past time is now happening at a different location, right? And the time and space difference between these two events is what gives us a notion of motion, right? So this video is one which is showing a positive movement, right, of the wave, right? The bend that originally happened at the left corner is slowly appearing to move to the right corner over different instances of time. If I were to reverse this video and play it in the opposite time scale, it will look like something is moving from right to left, right? So these things that we are calling as moving from left to right and right to left are the representations for V plus and V minus, okay?